Okay. Setting up. Are you going to join from there also?
No.
You're just going to be here? Okay.
But I'll have to update the link. So you have to send
Oh,
me
yeah.
the link right now.
Right. As soon as I have the link, I will send it to you. Here is the link. And I'll just put it up. Oh, I've got a. Are you going to join from there also? Okay, there we go. I had a little retroscope going on there. Did you get that link? Great. All right. You want me to tweet it also?
Please.
And then, oh, I guess I do have to have this open so we can see the chat, right?
Yeah.
It's my first YouTube live stream. All right. You guys might want to have that open to see the chat too.
You can pop it out into its own window so you don't have to keep the video open.
Oh shit.
Oh, you can? Okay, cool.
Just the YouTube chat.
Yeah.
Indeed.
Steven, you got the cool scroll background.
Yeah.
I like it.
So you're going to let people know.
Can you go to for sale and cancel the current deploy because it essentially put this in link.
Okay. Yeah. So I go here and deployments and cancel that one.
Yeah, I think so.
Okay. Cool. All right. I think we're going to get started in like 1 minute. Stephen, Seth, where are you two today?
I'm in the lab on campus.
And I'm in Virginia,
Oh,
living the
awesome.
dream. Yep.
Living the dream. I'm from Virginia. I think we did this before, but that's where I grew up.
Yep. Virginia Beach.
Nice.
Finally starting to get warm here. It's been unseasonably cold
Yeah.
the last couple of weeks.
Very rainy here. I think Stephen wins with the background. Look at that.
Yeah, I know.
Thanks.
Is that scroll 1 or scroll 2?
This, I believe, is scroll 1.
Scroll 1. Got it.
Here's the core there.
Very cool. And does this one not have an umbilicus in it? Is that what that looks like?
Not
It
in the
does
middle. I don't remember if it does near the ends. No, right?
Nope. I think scroll 2 has something that could be an umbilicus. It's kind of like hard and dense, but not all the way through.
Some of them that I've seen have in X-ray, it looks like little dense caps on either end, and then it looks like nothing in the middle.
Want to maybe go to the other
Want me to
stream thing and post this link to it?
post this link? Why don't I just kill it?
Yeah.
And we can. All right, everybody, please bear with us. This is our first. It's my first live stream, so definitely messed up in every possible way so far. Let's see, is this it? Content, and then live, and then we have to kill this one, right?
Yeah.
Actions, delete forever. Deleting is permanent. That's fine. Okay. So do you want to get started?
Well, do we have anyone?
Oh, that's a good question. Maybe there's nobody here. We have 6 people. Hello, 6 people who are watching. I think I'm one of them. Seth and Stephen may also be 3 people here, but we can get going. I think it's fine. So yeah, thanks everybody. Welcome to our live stream. I think we're going to try to do these just periodically for contestants and interested onlookers of the Vesuvius challenge, and use it as an opportunity to, I don't know, just answer people's questions, hopefully interesting technical and related questions about the challenge, and Maybe we can do like very quick, brief intros. I mean, essentially, I'm just going to kick this off. And I think we're incredibly lucky to have Seth and Stephen here, who are the actual like subject matter experts and responsible for all of the landmark recent achievements that make this challenge possible now, and we think tractable. And so, hopefully people are going to have a lot of questions for them. And then maybe JP, do you want to introduce yourself and
Yeah.
say hi?
I'm also just wondering, just for a sec before we do that, like how much
That's
of
a
a
stream.
time delay is there? Oh, I see.
It's just the stream lag. Yeah.
Oh,
it's normal.
wait, this is we're just okay all the way back. Okay,
Yeah.
great.
Do you want to say hello?
Yes. Hello, everyone. I'm JP. I'm sort of the project lead on the NAT side of things, or like on the Vesuvius challenge side of things. So over the last couple of months, I worked on putting together the website, the tutorials, working with Brent's team, Seth and Stephen in particular, getting the data ready together with Stephen, and like lots of stuff like that to kind of make sure that everyone kind of has a good experience coming into this, and can kind of get started quickly. My background is sort of all over the place. You can look me up online somewhere and learn more about me.
Cool.
I'm
Maybe
Stephen.
next. Stephen, go.
Yeah, my name's Stephen. I'm PhD candidate at the University of Kentucky and been working in this area for a few years now. So this is super exciting for us. We've been working on this research problem. We think it's super exciting. We've made a lot of progress recently that we're thrilled about, and we think is great timing to open this up and keep accelerating this work. And we want to read these scrolls. So excited that this has come together. Thanks for having me.
Yep. And I'm Seth Parker. I wear a lot of hats, but I guess I'm primarily the project manager at the Adduce Lab at Kentucky. And I've been working on this stuff since 2013. So actually, I think in March of 2013 was the first commit to volume cartographer. So we're like at the 10-year mark right about now. So pretty exciting.
Cool. So we've got questions coming in on the chat already. Why don't we, I'll just throw this to Stephen and Seth. The first one is from Ted, who asks, what do you anticipate will be the hardest areas of the challenge to solve?
I can give my answer, Seth, you can augment.
Yep.
But I think there are two. The goal here is to reveal the text from these rolled intact scrolls. They look like what you think of when you think of a scroll. And what we've done to date is validate a method to reveal the ink from scroll fragments, which are small pieces that are detached, right? And so two things have to happen to transition from what's been done to reading an entire scroll. And one of them is the ink detection we know works, but it has to be transferred to the scroll images, which are a slightly different image. They're at a slightly different resolution. There are other physical things that change when you switch from scanning a small fragment to an entire scroll. So the CT images just look different. And we need to be able to map the method that works for the fragments onto those images. That's one. And the other hard problem that I thought when I first started on this project looked honestly impossible, but I've been just continuously updating my belief that actually this is very doable. And that is the problem of segmentation, which is the three-dimensional tracing of these surfaces in the CT scan. So this is a scroll. It was once a flat sheet of papyrus. It was rolled up. Then it was crushed by 80 feet or 25 meters of ash. And so it's like taking a piece of paper and crumpling it up and sticking it in a CT scanner. So the structure in there is really complicated. It looks like a mess. The image behind me is a cross section of that structure in honestly one of its better areas. You can kind of see the spiral shape here, but in other places, even on this same scroll, it's a bit more of a mess. But what we've seen is when you look at this in the right way, so this is a cross section behind me, but if you rotate the cross section to be in line with the actual papyrus sheets, there's a ton of structure present in that data, and the papyrus sheets have this grid-like crosshatch pattern from the plant fibers, and it's all in here. You don't see it in that view, but it's in there if you're looking correctly. And we think by following those cues, actually the segmentation problem is going to be doable, but it's certainly challenging. There's a lot of related segmentation work out there in the world, but nothing quite like this. This is one of a kind. So it's a very cool problem, in my opinion.
Yeah, I want to echo both of those things. Obviously, the transference from the fragments to the scrolls is pretty important, because if that doesn't work, then you can't detect the ink in the scrolls, right? I'm very confident that it is transferable, that a lot of these things are, sort of locally quite similar across the scrolls, and that there's enough commonality between all of them that you're going to be able to learn something to detect the ink. So it's weird to think that that's the easier of the two problems, because I actually think that that's true. I actually think the segmentation at the moment appears to be harder, simply because it's difficult for us to see the signal that's available in these CT scans, right? Like we can, like Stephen was suggesting, you can reslice to look really locally at all the structure that's available, but seeing it all together is where you really want to be able to, get an intuition about what's going on. And it's just really difficult to see that. So I think somebody's going to figure out the right way to look at it to figure out what's going on. But at the moment, it's like the biggest unsolved part of the whole thing. So that segmentation is a huge thing. I do want to just shout out, though, that these things are not separate. Ink, we saw in our Discord yesterday, we've had this discussion before, that if you can detect the ink in the scroll without knowing where the surface is, that's actually a really good cue of where the surface is. There's ink on it. So, there can be a feedback loop here for all of you people out there thinking about ways to approach these problems. So
I want to add one more thing. We won't take this long on every question, but while we're still opening up,
very good question.
I think
it's important.
There's a principle that underlies both of those challenges that, to me, is why this data is so interesting and why we think this can be done, which is that there's a lot more in the data than our brains or eyes can make sense of.
Yes.
And you see that behind me. Like, this is a 3-dimensional volumetric scan. That's what you get with CT or computed tomography of any kind. Here, this is specifically X-ray micro CT, which means very high resolution using X-rays, right? It's volumetric. Our brains have no way of looking at that. We're reduced to cutting a slice through it and looking at it that way, or other things. So we're not that good at the segmentation problem because we can't quite see it all at once. And we have the same problem with the ink detection. We have not been able to look at this image with our eyes and tell you where there's ink. But we've shown that a convolutional neural network can do it. But there's so many moments of finding the right way of looking at things that, for us, that's been the sequence of sort of breakthroughs for us, and aha moments. It's like, oh, okay, if we just look at it in this new way, new information shows up, and we think that's going to continue. Yeah.
Let's see. Yeah. So there's a question of, for ink detection, how far off the mark do you think the Kaggle example code is? And just to clarify, I guess there's like several Kaggle examples at this point. There's the tutorial notebook, there's an example notebook, and then of course there's also the Ink ID program, which doesn't currently run on Kaggle, but which we've used as the baseline, and that's the baseline that you see if you go to the Kaggle leaderboard. It says Ink ID there. So those are sort of like the three things. Maybe Stephen can speak to that.
I think what we have right now between Ink ID, which is our solution we've developed in-house for this, and what we see on Kaggle, which today is mostly similarly inspired ideas. Where I think that stands is we've put in a lot of work to show that this can be done at all, and that we can take the images behind me and come up with some sort of geometry on which we can even run machine learning.
Mhm.
And we're really happy with where that is. That's a long pipeline that's taken us a long time to come up with. And we like that. What we have not really done is optimize very much the actual detection method. Ink ID that I've implemented is a pretty vanilla 3-dimensional CNN. It works much better than anything else ever has for this problem, but that's a huge explore or a huge search space of solutions that we haven't explored. We've been working kind of from the other end of this problem. So I think what we have now works. I think we will be able to come up with models and data augmentation methods and other refinements that will pretty dramatically improve the performance.
Yeah, I
Yeah,
think just in general, from a high level, I would say just adding on to that is just we're easily above chance in terms of like detecting where the ink actually is. We're not as good at like suppressing false positives, and I think that that's making readability quite bad. So in terms of just like what you think of as general metrics, that's where I think we are in terms of our current implementations.
yeah, you can also see on the tutorial 4 page, I think we actually show how Ink ID, how well it does with the actual outputs that it produces, which were, I think, created with like an n-fold or like a k-fold type training and then prediction. And you can really see that there's like areas where it does really well, where it can really see the ink, and other areas where somehow the ink signal is maybe different or not as strong. And so there's like, I think all of us are like really curious, like what is the upper limit here, right? Like how much signal really is there? And how much work is it to really get to a level where maybe you can see every single letter? Like that would be the ideal, right? And without any false positives, so that you can actually read it.
We did actually, for the first time recently, measure this in a few ways, and one of them that is the ultimate metric that I'm most excited about is we took some images that we generated and we gave them to papyrologists, who are the people who study papyrus, or they're the classicists who specialize in this material. So we gave them some images we had generated and asked them to make a transcription, which is, we know these things are Greek, so they know what language they're looking for. But they, based on the generated images, would write their estimated transcription. And then after that, we provided the ground truth images, which are infrared photographs of these same fragments. And then they transcribed those. So we could actually measure concretely where we are today. And where we are is between 40 and 50% recall on the characters. So what we have now gets almost half of them. So clear room for improvement.
Cool. Matt, do you want to say the next question?
Yeah, there was another question. Actually, this one came in on Discord, and someone said, I'm making, Scenaris, I believe, said, I'm making some good progress on a non-machine learning approach to ink detection using some custom image processing algorithms. Is that allowed? Can I still participate? And the answer is yeah, absolutely. Like if whatever works, you don't need to use machine learning. If you found another way, that's super interesting.
That's quite exciting, actually, if there are indeed ways. In fact, I think one thing that we've talked about is like maybe because we found that even relatively simple machine learning models can pick up on ink, which means, or at least it suggests that the ink signal is somewhat simple in some sense, or might be able to be found with other methods, and we just can't see it if you look at it directly. But we've also found examples, and Stephen has created a bunch of screenshots that we put in the tutorial number 4.
I'll share my screen and show those.
Yeah,
they're pretty cool. Maybe Stephen can narrate them a little bit.
Sure.
Yeah, of cases where you can actually see the ink directly in some rare cases. So
so these aren't all to the same exact scale. They're similar, but what we're seeing is on the left, these are images taken from essentially X-ray. These are the output of our entire virtual unwrapping pipeline, and we get what we call a texture image, which shows the surface as it appears in X-ray. And on the right, in each of these rows, there's an image that shows the same exact region, but from an infrared photograph of the surface. So in the infrared photograph, ink shows up quite clearly. In X-ray, it doesn't, which is why we're all here. But what we found is there are some places, they're rare, they're not enough to read the bulk of the text, but maybe 1% of the time, actually, you can see what appears to be ink quite clearly. So here, these arrows are all indicating shapes that I feel I was able to see quite clearly in the infrared and in X-ray, which suggests if the ink is thick enough or if it's contaminated enough in a certain region or whatever the case may be, there are places we can see it. The bottommost row is the most exciting. It is a little tricky to see at this scale perhaps, but Nat's cursor is kind of going over this chi or X shape. And what we saw on this fragment was only these characters. These come from a much larger fragment with a bunch of text on it, but only these 4 characters showed this pattern. And what we see if you're able to zoom in on that image, which you all can do at the website, is, or here we go. There's almost like, it looks like grains of sand in the ink. There's like little bright spots that show up. And yeah, the delta, iota, and chi in one stroke of this character in the top right all show up quite clearly, especially feel free to go to the website, download it, take a look yourself. So yeah, there are cases where things shows up.
Do you think there was some like particulate matter in the ink or something? What do you think that is? Do you have any idea?
So I don't know what it is, but one thing that's interesting about this fragment is elsewhere, probably on the website, there are photographs of the entire fragment and its surface. And what we see on this fragment is the entire surface has kind of dirt or sand on it.
Yeah.
I don't know if, yeah, there it is, fragment 2 right in the middle. You can see a big streak down the middle. That's like a strip of what looks to us like sand.
Yeah.
I'm not sure if that is ash from the eruption. That's my guess. Or if that was introduced during excavation or some later time period. But
This
we
is the
do see it
section
quite clearly.
right here.
That's
that
the
we-
section we were just looking at. Yeah.
Yeah.
So elsewhere on this fragment, we see all this dirt and sand. That also shows up quite clearly in the X-ray. But for the rest of those characters, there's no correlation between sand grains and text. There's just sand on the surface. I have no idea why it is on those characters. If it would have been in the ink while it was being written, or if it later adhered to the ink for some reason, it's not clear to me.
Got it.
I want to add to the
There's-
original question. We super welcome any methods, doesn't have to be machine learning. And we'd love to know what they are. Actually, feel free to reach out to us. You don't have to make it public. We won't share what you're up to for the purposes of the competition. But we're really curious because the only reason we're using machine learning for this is because we didn't find anything else yet that seemed to work.
Mhm.
But other methods, quite frankly, tell us more about what it is we're actually looking for. So that's awesome. Keep it coming.
Yeah, and it would be informative and useful in sort of for many things, right? Like we could build UI tools that sort of incorporate whatever computer vision algorithms you come up with, so you can look at things more clearly. Or if we sort of know what these features are, then if we ever go and scan more scrolls, it could be informative of like, this is sort of the resolution that we need because we now understand sort of the shapes of these features better. So for a lot of reasons, it would be quite useful to us.
Super useful.
and
We could add it as a
for the
filter
whole
to volume
community, of
cartographer.
Right, exactly.
Just generate a texture image that uses that principle and maybe it just makes the ink show up. That'd be incredible.
Yeah, I would actually suggest if for whoever is developing that method to go look at volume cartographer. A lot of it is just you pick a point in the 3D volume and construct a small region around it and then say, tell me if there's ink here based on that region. So your filter could just be applied straight inside of there. Yeah, it's all up on GitHub. Please reach out if you want to know how that works. For anyone who wants to use it, this is how we've done virtual unwrapping now for a decade. It was designed specifically so that people could add their own filters eventually. And we want that to happen. So please do that. I would love it.
Cool. Another question specific to Ink ID that came in from Matthew. He asks, what are the main, or do you know what the main errors of Ink ID are?
I can take a stab at that. There might be multiple ways to answer that. What I think of when I answer this is Ink ID is a simple machine learning model built on top of a sort of geometric software pipeline that we've come up with to do this processing. And we know for sure that each of those steps has room for improvement. So that's kind of how I would answer this is, we can measure the error at the end of the pipeline in the sense that we can generate an image and compare it with the ground truth and measure pixel metrics based on binary classification, or something more involved like having a papyrologist transcribe the image. So we can measure error, but I'm talking more, I guess, of sources of error. And there are there are at least three, probably more. So one of them is segmentation. That is where we start with the full CT scan of this fragment surface. Now the fragment surface is flat-ish compared to a rolled up scroll, but it's not flat. So we trace that as precisely as we're able with our current methods. And then we flatten it. That segmentation, initial segmentation, is not perfect. We're very happy with it. It's quite good, but there's always room for improvement. So that's one. Another is the alignment. And this, I think, might be among the bigger sources of error and areas for improvement. We generate from that segmentation a texture image that we were just talking about. So we use volume cartographer to generate an image that's sort of a flattened version of that surface in X-ray. And you see the papyrus fiber structure, you see the grid pattern, you see the shape of the fragment. In rare cases, you see ink like we were talking about, but you don't generally see much ink, which is the point, of course. So on top of that image, we align the infrared photograph, which becomes the label. That alignment is really tricky, and we're, again, happy with what we do today, but we know it could be better, that area for sure. That in computer vision, that problem of alignment is called image registration. And since these two images are from different domains, you would call this multimodal image registration. We have an infrared image and something sort of a composite thing we've made, but it comes from X-ray. They're very different. Different features show up in each one. That multimodal image registration problem is tough. Image registration is a big research area with many automated and well-established algorithms. We've tried a bunch of them, and we have not yet found a way to do this in an automated fashion. So actually, the way that we do that alignment is that I open those two images in Photoshop and I adjust the transparency between them 1,000 times, and I put on some good music and I sit there for a few hours and pull it into place manually. And the accuracy is pretty good that way. I mean, I find features like intersections of papyrus fibers, for example. I'll only put an alignment point if I'm quite certain it's a correspondence between the two. And I zoom in really close and it's quite accurate, but it's a manual process, known error for sure. Room for improvement. The last one is when we set this up as a binary classification problem, we take that infrared photo and again manually label which regions are so-called ink and which are not ink. We turn it into a binary problem for the purposes of simplifying the machine learning process and our own development. But in reality, things are a little more complicated. There's really thick ink, there's obviously not ink, and there's everything in between. There's places where there obviously was once ink and now the ink has chipped away and there's nothing. There are places where there obviously was once ink and now there's kind of chipped away, damaged, thin ink. There are places that are ink but have something else on top of it, like dirt or a fleck of papyrus. So it's not quite as binary as we've made it out to be. And in that labeling process, again, human process, there's probably error.
Yeah, I would also say to the point before that, the registration, the multimodal registration, that is something that we haven't really documented yet. So if anyone is kind of interested in that in particular, we can put in some more time and effort into making that clear. But I would say that if you go to the full data set, there are a bunch of files in there that are sort of the intermediate steps that Stephen used. So there's like a Photoshop file in there, there's various like mesh files, and I think they're numbered, so you can actually kind of go through them, open them in sort of the corresponding pieces of software, and then see, yeah, this is great, that is going.
I'm going to show it to you.
Yeah.
As soon as I.
That's a good point. Each of these steps you can find the file, the intermediate files from that step and fiddle with it yourself.
Yeah, here we
And
We go
I think
into,
maybe zoom in a little bit.
oh yeah, let me zoom in. Thanks. It's under working.
It's on the working.
Yeah.
Oh, it's not in scroll. It's for the fragments.
Okay, yep. Here we go, fragments.
Yeah, that one, for example, and then working. And then the exposed surface. Yeah, so here you can see 0001. So those are a bunch of different meshes. Maybe Stephen can actually speak to this better.
Yeah, the first few PLY files, those are all meshes, different stages of the segmentation process and then cleaning process. The 04 Poisson is kind of the final mesh. And the rest of these are images. So some of these are just sort of outputs from volume cartographer that you can likely ignore, like cell map. But there's an ink labels, that's the binary ink label image, the original infrared image there. There's a surface mask.
Yeah, and alignment.psd is the one where you actually did the registration, right?
Yes, thanks for pointing that out. That is correct. So that one you can open up and see all of my alignment points and improve them if you want. I'll also add result.obj. That is a mesh that contains the volume cartographer texture image. So you can actually open a three-dimensional mesh of the surface that has the X-ray surface sort of painted on it as a mesh texture.
We should
But
probably
you need,
document what all these files are on the data page.
Yeah.
I just
you need,
realized.
if you're getting the OBJ, you need the OBJ, the MTL, and the TIFF. Those three go together to make a surface.
Yeah.
Yeah,
it's just
we'll
the
document
OBJ
this.
format. But yeah.
Got it. Cool.
If anyone's in, like whoever asked, well, I guess this question started just sources of error. But if anyone finds interest in the alignment problem in particular, or really any of these steps, totally reach out. A lot of this is stuff that we have had thoughts on or are familiar with some other related work on, and just haven't had the bandwidth to do, or a small team. So a lot of this, we could give you pointers. There's exciting precedent in very similar alignment problems that we can point you to. We just haven't had time to explore it ourselves yet.
It would also be very interesting to gigapixel people, just because the resolution difference between photographs and the CT scans is pretty dramatic. Something like 4 or 5 times, and the photographs are already at like 600 or 800 DPI. It's pretty nuts. So anyway.
I'll just take a quick question that I'm qualified to answer from Joseph Jacks, who asks if the data sets are open source or on GitHub. The data sets are both not yet open source and also not on GitHub. They're huge. There's about 8 terabytes of data. And so we've rented some very expensive servers that you can use to download them.
They're very fast.
They're very fast. Yeah, we have an 80 gig uplink and like multiple NVMe drives rated. So you're just not going to be, your link is going to be the problem probably for getting this data, not ours. And we split the scroll data up into, you can download a giant tarball if you want, but like I would actually recommend not doing that and downloading the individual TIFF files, because you can massively parallelize your download very easily that way. And if you want to, you could choose to just download a subsegment of, in the case of the full scrolls. And so I think it's about 150 gigabytes per centimeter, roughly. And there's some scripts that we provide on the download registration page after you register, which you can use to do that. And so hopefully that'll help people do it. As to the open source question, currently, while the contest is running, there are terms on the download that you have to agree to. And that's to meet the requirements of all the various stakeholders and partners who are involved in this, including the conservators who granted access to the original physical artifacts to scan them. The intent is that after the contest has ended, to release all of that data under a Creative Commons license. But we won't be able to do that until after the contest is ended and hopefully successfully, and the decoding has occurred. So I think we're just incredibly grateful for the years of work that Dr. Seals and his team put into actually getting physical access to these artifacts and actually producing these incredibly high quality scans, and then the tools that allow people to start to work with them. And I think, I think this is a great arrangement. putting them on GitHub. Unfortunately, GitHub LFS support is not sufficient to the task of both hosting and providing economically efficient downloads of this stuff. In fact, when we were trying to figure out how to make it downloadable, we thought we'd put it in like a bucket on AWS S3 or GCP or something. And then we calculated that each download would cost us something like $500 to $1,000.
Yeah.
And we were like, wow, they really get you an egress in these clouds. So we had to do something else. So anyway, we think that you should be unconstrained in terms of bandwidth capacity. And, if anybody has trouble, let us know, I guess.
Yeah, well said.
Cool.
Let's see what other questions are there. How stuck do you feel?
It's a good question.
Yeah. Does it still feel
That's a good
like
question.
everyone, like if we have ideas for things that we might try if we have given enough time, I guess?
I'm happy to answer that. Seth, you're smiling.
Well, yeah, I mean, for people who don't know, this is Stephen's dissertation work, so I don't know how much of his
That's true.
ideas he wants to give away.
That's true. Well, I'm not a formal competitor, but we're still working on this problem. Yes.
Yeah.
I actually feel not stuck at all, and that has not been true the whole time we worked on this. There have been many moments of feeling very stuck. Some of them predate me. Like Dr. Seals has felt very stuck on this problem years ago. I've spent about 5 years now working on this problem, and there have been moments where, yeah, we haven't known what to do next. That is not true right now. Actually, we're making really good progress on this. One area we're really excited about is just in the last few months, we have revealed some hidden characters from the fragments for the first time. Now, there's a long way to go from that to reading the entire scroll, which of course is the goal here. But to us, that represents a huge technical breakthrough. It's really exciting because it has taken a long time to get past 0. And now we're past 0, and the text that we've recovered from those fragments, though again, quantities remain small, but it's growing. It's actually moving the needle now. That's thrilling to us. And you can see in the fragment data that we've released, if you download just the surface volumes, those are the smaller data sets that follow the surface only. Those don't contain the hidden layers of those fragments. But if you download the full scans of those fragments, which are a couple hundred gigs each, you can see in the cross-section, each of those fragments actually has an exposed surface with text on it, but also multiple layers. They're not so much like one sheet of papyrus peeled off. It's like a chunk came off. So you actually get a top layer and then multiple sublayers. And we've started with the lowest hanging fruit. We've start with the easiest ones to segment. We've done a handful of those. We've recovered on the order of 5 to 10 Greek characters that were not seen in 2,000 years. And in the last couple of months, we've revealed them, and we're thrilled about that. And we're kind of chipping away at that. We're chipping away at trying to get this to map to the full scrolls. There are multiple challenges there, but
can you
not stuck at all, really.
Yeah, my take on that is if this were just left to Dr. Seals and Stephen and Seth, it would get done. But it might take a while. And I think the idea of the contest is hopefully to speed that up. And I think we also think it's fun to do a contest.
100%.
Yeah, I mean, also part of the question is sort of any suggestions, like what are some of the ideas that have been brewing? Should we make
yeah, well, I wanted to say one other thing. I don't know if Stephen could say, please feel free to pass, but would you care to share what the first characters were that you unveiled in the hidden layer? Yeah,
and it's all in the paper, which you can find on our GitHub. So the first 2 characters, one of them is clearly a Greek eta, which looks like an English capital H. And below it on another line is a vertical stroke that could be from a number of characters, but it kind of looks like possibly if it's just that one stroke, it would be an iota, which kind of looks like an English I. So visually, and this is Greek, it's not English, but visually it looks like it just says hi.
It
is
truly
like-
is
that
the
is-
hello world of the Vesuvius challenge. Or of
Yeah,
the-
it was kind of hard to believe. Like that was the ultimate message we've been working for years to decode. Like the first two
Hi.
characters say hi. Yeah. And since then we've come up with some more. They aren't quite as fun as hi, but yeah, you can look at all of it in the paper.
A couple of people have asked about sort of academic publications, and I think maybe in our last minute editorial pass on the website, we may have accidentally removed some information about the plans there, but the intent is basically for the winning team to be co-authors on a paper with the UK team about this. And I think that's actually part of the actually, it is in the agreement that people agree to when they register for the competition and download the scroll. So it's a qualifying criteria that you would do that. And so if you win, yeah, you get to, and you are required to co-author a paper on the huge achievement. I don't know if Stephen or Seth want to add anything to that.
Yeah, I would just say we're huge fans of people getting credit for their work. Academics is really built on people, and science is built on people sharing their results and working together to find solutions to things. And we don't want you to go and do all the work and us take all the credit. Like, you did the work, so you deserve the credit. So absolutely, I would jump at the opportunity to work with whoever wins the contest. And let me just say, I think we're interested enough that it's possible we would want to do things that don't win the competition. We'd want to do publications around methods that don't win the competition simply because they're interesting. So don't think we're ruling that out if you don't win. We want this field to grow, and that only happens if people come up with cool new ideas.
And someone else asked, does the competition end December 31st, or kind of what's the deal there? Yeah, I think the grand prize can be claimed at any time. I mean, it could happen tomorrow. If someone were to submit a qualifying result and it kind of passed review of the review team, then we'd be a little bit surprised, but I think we'd be very excited to award.
Yeah, it would be incredible.
It would be incredible.
Right?
Yeah, it would be
Yeah.
amazing. We are thinking about, because we got so many donations this week, we are thinking about maybe adding on some. We haven't figured out what this is yet. In fact, the group of us have not even been able to discuss it yet, but we are thinking about maybe adding on some kind of like extra prize for the best, decoding by the end of the year or something like that. So the grand prize only requires 4 passages, and we think there's probably more than 4 passages in there. And so
4 tweets.
Yeah, four passages of 140 characters each, which we didn't realize when we established those that rubric that is basically the equivalent of finding 4 tweets in the scrolls. But there's probably more in there, and so it might be cool to have another prize. So you have a kind of first prize and a best prize. TBD. I think we have to discuss it and see. But it would be nice to have some stretch goals in here, especially now that we have this huge war chest that we were sort of shocked to get a few days ago this week, with all the incredible contributions from people, including Joseph Jacks, who's here in the live stream, and in fact, who I have to go have lunch with right now. So I'm a little bit late. But yeah. So I'm going to jump out. I'll leave you with JP and Stephen and Seth. See you guys.
Thanks, Nat.
I'm gonna answer really quick. How did you convince the team already working on this to open source their data? Well, we are the team who are doing it. Nat convinced us, I would say, primarily because we were already interested, but we didn't know how, right? Like we don't want to just hold on to this and keep it to ourselves forever. But it's also on it. We have 8 terabytes in the competition. There are hundreds of terabytes in our archive of data that people could have. We do not have the capacity to process that data, to give it out to people, to do whatever. So part of this competition was a forcing function of, Nat and JP have been excellent around organizing the competition and helping us figure out some of these very practical problems of making the data available. And we wanted it to be available anyway. So that's how they convinced us, and how we convinced each other, I think, that, it was finally time.
I agree. I'm smiling at this question coming in. I was going to add to that. Yeah, we are excited about this data, have been for a long time. We think this particular research problem with the Herculaneum scrolls, but also more generally this line of work, is just interesting. It's something that kind of belongs to everyone and should be open. And, you know, there's also, we're thinking a bit aspirationally here, like we believe and hope this will be solved. And when that happens, the methods have to be verifiable. Like the stakes are kind of high for this collection in particular. If you just say, oh yeah, we read it and here's what it says. Because you or I could go Photoshop something right now and make up whatever Greek text we want and say, hey, we solved it, here's what the scroll says. That's not gonna fly. Like this is too interesting of a thing. It needs to be a community effort that's reproducible and people need to believe that it's legit. So open source the whole way is kind of the approach that we think makes sense.
Do you want to take the clones? The clones.
Let me think about that. Is there anything else either of you can?
Yeah, there's another question that we kind of skipped over earlier, which is, would it be cheating to use an LLM to help anticipate what the next word, I guess, will be, and combining that with raw ink data could lead to hallucinating results? I think, yeah, I'll take a first pass on that. Like that is one of the reasons that we so explicitly mentioned on the website and in the terms that you have to guard against hallucination, because if your model really understands like what Greek texts look like or Latin texts look like, it can just start making up stuff, right? And so I think that it could help in maybe filling in gaps between things, but we probably don't want it to, start coming up with entire texts. And also, to some degree, like in some sense, the papyrologists can also fill in those gaps, right? So if we might not need it in order to kind of come up with sort of a coherent story of like, okay, we can see these characters and how do you infer like what the whole text would look like from that? Because like that is basically what papyrologists do, right? Like they get like very damaged texts and they're able to really extrapolate quite a lot from that with
professional jigsaw puzzlers.
Yeah, exactly.
And I have a sort of separate concern about this. We thought a lot very early on in Volume Cartographer with some of our other work about how we formulated the problem, and we picked ink detection as opposed to character detection or text detection, specifically because two reasons. One is it's more objective. None of us on the team, on the technical team, read Greek, read Latin. We ask other people if they see these characters. And that's sort of like a protection for us. We can't hallucinate seeing the character because we don't know the language. And when you hallucinate a word, it has to make sense. Like if I just hallucinated a bunch of random characters, but I don't know what they are and doesn't make a word, then, clearly I haven't read anything because I've just made stuff up. So that's one reason. The other is not all of the content is text in these documents, right? People don't just put characters in. They can draw pictures, diacritics. There's all sorts of things that are not characters that could be inside a scroll. And we don't want to just limit ourselves to text because there's much more available inside these manuscripts than just that. So
that's a great point.
Yeah, as a brief aside to that, just because I don't know that we've talked about this elsewhere. One thing you see quite a bit on these is called supralinear ink, and that's markings in between the lines of text. And sometimes it's corrections, sometimes it's accent characters. The specific meaning of those markings, I'm not the person to answer that question, but it's deliberate ink marks that show up in unexpected places to an untrained eye like me. They're not in the normal line. We actually see a lot of that. You'll see it in our label images. That's supposed to be there. And I also wanted to add that, yeah, we try to separate these problems. We're working in the space of ink detection. So we want to generate images that to us looks like some text is starting to appear, and then we're hands off. We pass that to the people who read the text. But in elsewhere in machine learning and heritage, it's someone's job to parse a bunch of text, and not only this collection, but all kinds of different collections of these materials. And there's actually really interesting work that does use something more resembling a language model to help the papyrologist do that. And it's super interesting. Someday we would love for that, we want to generate enough text with these scrolls that sort of thing comes into play. Today, it's not really necessary. But yeah, very interesting problem. We try to keep them separate today, but who knows?
There's also there's a question about Kaggle's public leaderboard, which I'll just quickly take. It says, since the training set contains test data, it should be easy to make a submission that gets a 1.0 score. So I just want to clarify sort of the training and the test data on Kaggle. So the way that is set up is that if you look at the public data set on Kaggle, the test data is actually just a subset of the training data. It's like fragment one split into two pieces. But when you actually make a submission, we substitute that test directory for like a secret test directory that contains the fourth fragment, which we haven't made public. And so exactly. So when you look when you do the submission, your program will run on that. And I think that the submission notebook doesn't have access to the internet, so you can't just send it to yourself and then get like a perfect score that way. So that is the way that is set up.
And I just want to clarify too that when even in your own testing, if you have a test and train of two different parts of the same fragment, like locally, if you pick any particular pixel in each of those images and look at the associated CT data with that pixel, they're going to be drastically different. Like they're from the same fragment, but they're not exactly the same. So it's not like you're training on something you've seen before in the same way that you would be in other tasks necessarily.
Right. Let's see. Do we want to take the clone question?
I'm ready. I'm ready.
I'm also I can share my thoughts on.
We could all answer that.
Yeah. Do you want to start then?
Got an idea?
Sure. I'm going to give my 5. Person 1, get on Kaggle and maximize the performance of the ink detection under its existing construction. Person 2, come up with methods, maybe even manual, not very intelligent methods to do segmentation on the low-hanging fruit parts of the big scrolls. Person 3, start thinking about more intelligent, more sophisticated methods to do the segmentation on the entire scroll, which we know will not be doable entirely manually. Small parts of it, yes. The whole thing, no. Person 4, think about the domain transfer. You need to be able to take images from a fragment and make them look like they came from inside a scroll or vice versa to get the models trained on fragments to work on the in-text scrolls. And person 5, see if you can shake up our pipeline somehow. We've arranged this as this sequence of steps in a way that is somewhat historical, somewhat makes sense to us. But we know these can be reordered, or possibly some of them can be condensed into single steps. And what we've seen a lot in sort of tangentially related areas of computer vision and language models, and all of these areas we're seeing a replacement of what was once an intricate handmade pipeline with just a big smart model, right? Or we see what was once 8 steps, you can take 3 of them. Now one learned method does all 3 of those, and we're just seeing things get condensed like that. All right, that's my team of 5. That's what I'm sending them to do.
I don't know that I have 5. First, I just want to shout out to an inside joke between Stephen and I. We have the same initials, SP, and we've often joked about what you would do if you have more SPUs instead of CPUs in just our time.
Well, our advisor is always asking us
question.
if we need, what do we need? Do we need more CPUs, GPUs?
GPUs.
Like, no, we need.
And
more
our answer is
CPUs.
always need more SPUs. So I
So
love
that's
this
what the
question in
contest
principle.
is.
Yeah. Yeah, I mean, mine are very, very similar to Stephen's. I think I'm much more interested in just learning what the nature of the signal is. I've been so involved on the scanning side of all of these projects in the last 5 years that I haven't really spent a lot of time on the processing, not as much as Stephen has been doing. And I see one of the long-term things we want to figure out is how can we bring the resolution barrier down? Like right now, we're providing you with data sets at 4 microns and 8 microns. And we had to go to a synchrotron to get that. And
it was barely possible.
And it was barely possible, not because it's not technically possible. It's where the way we want to scan these things, it's like the only thing that you'd ever want to scan this way. So things just aren't set up to do this type of scanning at this type of resolution. These are relatively large objects for the resolutions we're scanning at. And they're, 15 centimeters long or something. Tops. It's not
everything just breaks when you try to do that.
Everything just breaks. Yeah. So for instance, the final process data sets are 8 terabytes or whatever. When we went and did the scan session, we walked away with 180 terabytes of data that we had to figure out how to get from England to our server in Kentucky. It took months just to figure out the right way to do that. Anyway, all of that to say, like the resolution barrier is really difficult just for machine learning, for processing, and I want to know what the signal is so we can lower that barrier and do this work at things that are more achievable in regular CT scanners or regular micro CT scanners. There's a lot of great instruments out there for doing this stuff, but not at the scale we're currently working at. So that's what I would focus all 5 of my people on, is just like, how can we make that all better? But yeah, Stephen is pointing out our new CT scanner just behind him there that we just got for our lab. It's technically not even functional yet, but yeah. That's what we're going to start doing more scanning on soon. So
yeah, we want to be able to put them in there and read them.
Yep.
Let's see, what would I have 5 JPs do? I think one of them I would have built like more UI tooling for sort of slicing this stuff. Right, like we've been like in the tutorials we use Fiji/ImageJ, which just can't handle this amount of data. Like it just, even the campfire scroll, which is like which I even had to kind of bring down in terms of resolution so that you can even load it in ImageJ. Already there it's struggling on my machine, and it's like an expensive machine. So there's no way you can just like straight up load like terabytes of image stacks in there. So that and I think that would just be quite useful, right? Like if you see those pictures that Stephen found sort of along the way of where you can just really see the ink. If we can just sort of, slice things more easily, maybe we can just see more of those, with our monkey eyes. So that's JP1. JP2.
Maybe web-based stuff.
Yeah, maybe web-based stuff even. Yeah, so there's a lot that can be done there, I think. JP2 would probably, like work on the ink detection, Kaggle price, and maybe to Stephen's point, there's like shaking up the stack. In particular, something that I would be interested in looking at is skipping sort of the surface volume step, because the subsampling of the original volume around the mesh that sort of describes where the papyrus surface is into a new volume around that just introduces error.
I should have included that in my list of error introducing steps, because that's
right. No, that's a good point. Yeah, so skipping that or like sampling directly from the original volume, maybe you take into account orientation somehow, but doing something there that's kind of makes it so that you don't introduce that error, I think could be quite interesting. Unfortunately, we can't really do that on Kaggle right now because you would need access to the original volume, which is like very large. It's a bit too large for Kaggle currently, but you can kind of do this offline and just see if you can get better results there. That's JP2. Let's see. JP3 would maybe, I don't know, make a campfire scroll and see if I can find like someone in my neighborhood who has like a CT scanner somehow, or like a university who I can coax into getting some CT scanning time on, and just kind of see if I can create more ground truth data by creating my own skulls, and kind of seeing like, would that help? Let's see, JP4 would maybe, actually, to Seth's point of like resolution, do more experiments with like actually reducing the resolution of what we have right now, and kind of seeing like at what point does it start breaking down? Like, are there some graphs that we can create, right? Like okay, this is sort of, the point where you really see like metrics like breaking down if you sort of reduce the resolution to that point. I think that could be very interesting. And I think JP5 would try to do what this person did that we talked about earlier, trying to kind of get at it in a non-machine learning way. And the way I would probably try to do it is see if there's some way I could sort of reverse engineer the machine learning models, or kind of see what they're picking up on. Maybe you can, I don't know, do some sort of generative thing, right? Where you have your machine learning model trained, and you inverse it, where you see, okay, where do I get like the, for what inputs do I get like the biggest stimulus? And then maybe see like, okay, are there some features that we can see with more traditional methods within that? So that we just get a better understanding of like, what are these features, right? Because it's it just feels like it should be possible to see these things more easily. And then, you connect that with the UI tools that at this point JP1 has built, and integrate it there, and maybe you can just see the text. That would be the
you actually made me realize a thing I would want one of the other me's to do, which basically is a lot of what you touched on. What, like, when we started Volume Cartographer, it was before the big machine learning boom, and I would go back and re-implement that library in Python. And where we thought we needed a ton of performance at the time, so we did it in C++. Now you can do all the fun interface stuff in Python that you really want to do, integrate it with machine learning a lot easier. And if you need performance, you use Python, and that's just, great. And that would make things like better UIs a lot more easier to do, integration with machine learning a lot easier. We have a lot of stuff in Volume Cartographer for like caching of the volume that we just can't really use in IncID directly. So like, there's all sorts of things that we had that I would love to be able to transfer into machine learning. So if anybody wants to just do that, please do. I would
there's a bunch of cool, like, just software engineering that as a university team we haven't been quite equipped to do, but that we're ready to. We'll take all these ideas and we'll make a list, and anyone interested can come sign up, because there's a bunch of cool stuff to be done.
Yep.
Cool. Let's see. I think we can close it out. Maybe one last question. There's maybe two nice questions to close out with. I have a question about the models you used in the article that gave 0.51 in Kaggle. Are you planning to give more information about this model used? So that's IncID. Stephen, do you want to just quickly mention what that is?
Absolutely. The code is available today on GitHub, EduceLab IncID. That should be linked somewhere from the Scroll Prize website if you go in the resources page, right? So the code's available. The method has been written about in a prior paper that sort of introduced this concept in PLOS 1. That paper is probably also linked from the Scroll Prize website. And then the paper that we have just put a preprint of online. I'm working on the methods section, which will be what you are asking for, essentially. But that part of it, the model itself, is very minimally, if at all, changed from the PLOS 1 paper.
Yeah, and I would say, like, we currently don't run that in Kaggle. Like, we weren't able to in time kind of create an example notebook that has like the original IncID program in there. But if someone wants to give that a shot, it should be possible. So that could also be an interesting contribution. And then there's like one more question about how did we choose these unrolled fragments rather than others? I think that's mostly like we had access to them, or like you guys had access to
Yeah,
them.
yeah. I'll answer that. Stephen can chime in too. So the tough thing about working with any cultural heritage object is you have to convince someone to let you do work on it. Because if you destroy it, there's nothing to work with for anyone ever again. So we've spent a lot of time just building relationships with lots of partner institutions for people who have the Herculaneum scrolls. They're spread across 3 or 4 different institutions, and we now have good relationships with all of those. So like that is just primarily how we start anything, is just build the relationship so we actually have access to the materials. For the scan session specifically, there was one institute, the Institut de France in Paris, who had materials that they were willing to let travel to the diamond beam line at the time that we needed them. So like it just happened to converge at the right time that they were the ones that we got fragments from. Now, in terms of actual selection of fragments, we did a whole pre-scan interval where we went and photographed all of their open fragments. And then we reviewed
probably
them
hundreds, right?
Hundreds and hundreds of fragments that we then reviewed to select. We knew we had about enough time that we could do probably 4 fragments. So we selected the 4 fragments that we thought had the most characters on them. And the idea was that would give us the best representation of the variation in the ink across those fragments. So
yeah, biggest training data set.
Biggest training data set. So it gives us like the fragment size plus the number of characters. There's a whole metric spreadsheet we worked up to try to like rank these things. And then just clarity of the photographs that we had of what do we think could give us good label sets. So that's how we selected the 4 we had. Related to that is the next question, is there a selection effect? Maybe. Like part of the problem here is we don't know what it's like inside a scroll until we've physically opened it. And then once you physically opened it, it's a different thing. So we're making some pretty strong assumptions, not strong assumptions. I think they're pretty similar, but I think we're making some assumptions that once you open the scroll, the similarities are enough that you're going to overcome any sort of selection effect you might have by learning off of these opened things. But, you know, it's unknown at this point exactly how much problem that introduces when you unroll them.
Yeah. I was thinking of another way of answering that, which is, was there any motivation behind some scrolls having been unrolled already and some not?
Yes.
And we don't, someone may know this for sure. I don't know this as a fact, but I think it's pretty well understood that they unrolled the easiest ones first. So we're left with the hard ones. Yeah, basically.
Yes. Yes, that is true.
Cool. Well,
it is what it is.
Let's wrap this up. Thanks everyone for great questions. And yeah, if this was useful, maybe we'll do some more. So, you know, think of more questions. We're also hanging out in Discord all the time. So, you know, just fire away and we'll try to answer any question that you have there. Yeah, and thanks to Seth and Stephen for joining us. This is awesome.
Thank you, JP. And yeah, thanks everyone for participating. This is so exciting for us. So cool.